Here's something that shouldn't be possible. Light has no mass, not a little mass, none, zero. And yet, right now, somewhere above your head, starlight is bending around objects it should have no reason to notice at all. It's happening around the sun, it's happening around galaxies billions of light years away. It's happening around black holes so dense that space itself folds in on them. And for over a century, this one fact has quietly broken one of the oldest rules in physics. The rule that says gravity only pulls on things that have mass. So how does something with zero mass get grabbed by gravity at all? Stay with this one, because the answer isn't a theory anymore, it's a photograph. And you're about to see exactly how we took it. Let's start with the rule you were probably taught in school, because it's the rule that makes this whole thing feel impossible in the first place. Isaac Newton gave the world a picture of gravity that works so well it put men on the moon using math he wrote by candlelight. In that picture, gravity is a force, an invisible rope between two masses pulling them toward each other. The bigger the mass, the stronger the pull. Simple, clean, and completely dependent on one thing. You need mass on both ends of the rope for the pulling to happen. That's the part that matters here. No mass, no rope. No rope, no pull. Light has no mass. A photon, the particle of light, has exactly zero rest mass, confirmed by measurements so precise that if a photon had even a whisper of mass, our GPS satellites would drift out of sync within days. So under Newton's rules, light should sail past a star, a planet, a black hole, completely untouched. No rope to grab it, no pull to bend it. Light should go dead straight forever, no matter what it flies past. Except it doesn't. And the first person to seriously ask why not was Albert Einstein, sitting in a patent office in Switzerland, not a laboratory, thinking about something that had nothing to do with light at first. He was thinking about falling. Here's the thought experiment that started all of it, and I want you to actually picture this with me. Imagine you're in a sealed elevator, no windows, floating in deep space, far from any planet. If someone starts the elevator accelerating upward, you'd feel your feet press into the floor. You'd feel weight. Now imagine that same elevator sitting still on the surface of a planet with gravity. You'd feel the exact same thing. Same pressure on your feet, same sensation of weight. Einstein's question was brutally simple. If you can't tell the difference between accelerating through space and sitting still in gravity, maybe they're not actually different things. Maybe gravity isn't a force pulling on you. Maybe it's acceleration in disguise. Now here's where it gets strange, and where the light problem walks back into the story. If you shine a flashlight sideways across that accelerating elevator, the beam of light will appear to curve downward, toward the floor. Not because light suddenly weighs something, but because the elevator itself is accelerating up to meet it, while the light crosses the room. The light goes perfectly straight, the room bends around it. And if accelerating rooms and gravity are secretly the same thing, then a room sitting on a planet should do the exact same thing to light. Gravity doesn't need to grab light with a rope. Gravity needs to bend the room. That's the reframe. Gravity isn't pulling on light. Gravity is bending the space that light is forced to travel through. Light isn't taking a curved path because a force yanked it off course. Light is taking the straightest possible path available, and the space itself has been warped into a curve. Imagine drawing a straight line on a flat sheet of paper, then draping that paper over a bowling ball. The line still goes as straight as it possibly can along the surface, but from the outside it looks bent. That's what a massive object does to the space around it. It's not lying to the light. It's rewriting the map the light has to follow. I know what a lot of you are thinking right now, because it's the single most common misconception about this whole topic, and I want to correct it directly before we go any further. Gravitational lensing does not mean gravity is grabbing photons the way a magnet grabs iron filings. There's no grip, no force reaching out and hooking onto the light. The light is doing exactly what it always does, moving in a straight line at the fastest possible speed. It's the space it's moving through that's no longer flat. Get that one distinction right, and the rest of this stops being confusing and starts being obvious. There's a second misconception worth clearing up while we're here, because it trips up almost as many people. This isn't about light slowing down near massive objects, the way light slows down passing through glass or water. The speed of light in a vacuum stays exactly what it's always been. What changes is the shape of the path, not the speed along it. A photon near a black hole is still moving at the same fundamental speed it always moves at. It's the geometry underneath it that's been rewritten. Keep those two things separate, speed and shape, and you'll never confuse this topic with an ordinary optical trick like refraction again. It also helps to know this wasn't even Einstein's first attempt at the answer. Back in 1911, using an earlier, incomplete version of his theory, a version that only accounted for time being walked by gravity, not space itself, he calculated a bending value for starlight. It was a real, published number, and astronomers took it seriously enough to plan an expedition around it. It was also wrong, by almost exactly a factor of 2, because it was missing half the picture. It took Einstein another 4 years of work and a full reworking of the mathematics of curved space to arrive at the number that would eventually get tested in 1919. I bring this up because it matters for how you should think about science actually working. Even Einstein got his own idea wrong once, published it, and had to correct himself before the version that finally held up against reality. That's not a weakness in this story. That's what real scientific progress looks like from the inside, long before the headlines arrive. So Einstein had the idea by 1907, refined it through 1911, and by 1915 he had turned it into a full mathematical theory, general relativity. But an idea, even a beautiful one, is not proof, and Einstein knew that better than anyone. He made a prediction so specific, so testable, that it could have ended his entire theory in one afternoon. He calculated exactly how much starlight passing near the sun should bend, due to the sun's gravity warping the space around it. And here's the part that should make you sit up. Newton's older theory, if you forced it to make a prediction using light as if it somehow had a tiny mass, gave you a number. Einstein's theory gave you a different number, almost exactly double. Two competing theories, two different, precise, falsifiable answers. Only one could be right. Now think about what that actually means for a moment. This wasn't a vague philosophical debate you could argue about over coffee forever. This was a number, a measurable angle in arcseconds that starlight should bend by. If you could photograph stars near the sun's edge and measure exactly how much their position shifted, you'd have your answer. Einstein was either about to be immortalized or about to be humiliated by a Swiss patent clerk's science fiction idea about warped space. There was just one enormous problem. You cannot normally see stars anywhere near the sun. The sun is blindingly bright. Its glare drowns out every star for millions of miles around it. There was exactly one moment in nature when this experiment became possible. A total solar eclipse, when the moon blocks the sun completely and for a few minutes in the middle of the day, stars become visible right at the sun's edge. And here's where the story gets genuinely dramatic, because this test almost never happened at all. The first attempt was in 1914 in Crimea, led by a German astronomer named Erwin Freundlich. World War I broke out weeks before the eclipse. Freundlich and his team were literally arrested as enemy nationals on Russian soil and their equipment confiscated. The eclipse happened without them. In hindsight, that failure may have saved Einstein's reputation, because his gravity math wasn't finished yet in 1914, and if that expedition had succeeded with the equipment intact, it would have tested an incomplete, incorrect version of his theory. The real test came in 1919. The war had just ended. Europe was exhausted, fractured, and in that atmosphere, a British astronomer named Arthur Eddington organized 2 expeditions to observe a total solar eclipse, one to the island of Príncipe off the coast of West Africa, and one to Sobral in Brazil. Think about the symbolism here for a second, because it's not incidental to the story. British scientists mounting an expedition to test a German physicist's theory, less than a year after Britain and Germany had been trying to destroy each other. Eddington, a Quaker and a pacifist, saw this as something bigger than physics. He saw it as a chance to prove that truth doesn't have a nationality. There was real personal risk in this for Eddington too, and it rarely makes it into the retelling. As a conscientious objector during the war, he had faced pressure to be conscripted, and it was only the intervention of the Astronomer Royal, arguing that Eddington's scientific work served the national interest, that kept him out of the trenches, on the condition that he led exactly this kind of expedition once the war ended. So when Eddington sailed for Príncipe in 1919, he wasn't just testing a foreign physicist's theory out of curiosity. He was, in a very real sense, spending the credibility he'd been granted instead of conscription on proving that international scientific truth mattered more than wartime nationalism. If the expedition had failed or found nothing conclusive, it wouldn't have just been a quiet null result. It would have been a very public, very personal disappointment in front of a scientific establishment that had taken a chance on him. On May 29, 1919, the moon's shadow swept across the Atlantic. In Príncipe, the weather was terrible, clouds rolling in and out, threatening to ruin months of preparation in minutes. Eddington's team managed to capture a handful of usable photographic plates through gaps in the cloud cover. In Sobral, the skies were clearer, and a second team captured their own set of plates. Now came the part that took months, not minutes, comparing the position of the stars in these eclipse photographs against photographs of the same stars taken at night, when the sun wasn't there to bend anything. If the star positions matched exactly, Einstein was wrong, and Newton's simpler picture stood. If the stars had shifted by Newton's smaller predicted amount, gravity was pulling light like any other force with mass. And if they'd shifted by Einstein's number, almost double, then space itself was curved, and one of the strangest ideas in the history of science was real. In November 1919, the Royal Society and the Royal Astronomical Society held a joint meeting in London to announce the results. The measurements matched Einstein, not Newton's number, Einstein's number. The Astronomer Royal at the time, Frank Watson Dyson, described it as one of the most significant results in the history of scientific investigation. The next morning, newspapers around the world ran the story. The Times of London put it on the front page. The New York Times ran a headline about lights all askew in the heavens. Almost overnight, a physicist most of the public had never heard of became the most famous scientist alive. Picture that shift for a second. A man who 6 years earlier was doing physics as a side project while stamping patent applications for a living, now had his name in headlines across 2 continents, because Starlight bent exactly the amount his equation said it would, and not the amount anyone's intuition expected. But, and this is the part most retellings skip, the 1919 results weren't actually as clean as the headlines made them sound. The Principe data, heard by clouds, had larger uncertainties than scientists would like today. Some historians have pointed out that Eddington may have leaned toward the data that supported the theory he already believed in. This isn't a scandal, and it doesn't undo what happened, but it's the honest, less flattering footnote that deserves to be part of the record. Science doesn't get to skip its own messy middle just because the ending turned out to be correct. So here's a fair question, and if you're the skeptical type, you're probably already asking it. If the original 1919 evidence was shaky, why should you trust any of this today? Because 1919 wasn't the last time we checked, it was the first. And every decade since, the checking has gotten dramatically more precise and dramatically harder to explain away. In the decades after Eddington, astronomers found something even stranger than a slight bend in starlight. They found rings. When a distant galaxy sits almost perfectly behind a massive object, like another galaxy or a cluster of galaxies, the light from the background galaxy doesn't just bend a little to one side. It bends all the way around the object in front of it, forming a full or partial circle of light called an Einstein ring. Einstein himself, in a 1936 paper, calculated that this should theoretically be possible, but doubted anyone would ever have a telescope powerful enough or find a cosmic alignment perfect enough to actually see one. He was wrong about that too. The Hubble Space Telescope and, more recently, the James Webb Space Telescope have photographed dozens of these rings, glowing circles of bent starlight, hanging in deep space, exactly where the math said they'd be. Now here's a question worth pausing on before I answer it. If gravity can bend light into a perfect circle, what do you think happens if the object doing the bending isn't neat and symmetrical, but lumpy, uneven, scattered across a huge area like an entire cluster of galaxies? Take a second and guess. Because the answer became one of astronomy's most powerful tools and one of its strangest discoveries. The answer is that the light doesn't form a clean ring at all. It gets smeared, duplicated, and warped into arcs and multiple distorted images of the same background galaxy, scattered around the cluster like a funhouse mirror. Astronomers realized they could use this distortion like a piece of forensic evidence. By carefully measuring exactly how much the light bends and where, they can calculate the total mass of the galaxy cluster doing the bending. And here's the reality check that changed cosmology. When astronomers did this math on real galaxy clusters, the amount of mass required to bend light that much was far greater than all the visible stars, gas, and galaxies combined could account for. There had to be something else out there, massive, invisible, and detectable only by how it bends light. Today we call that missing mass dark matter, and gravitational lensing remains one of our primary tools for mapping where it hides. This is worth sitting with for a second, because it's easy to let it fly past as just another fact. We are mapping something we have never directly seen, something that emits no light, reflects no light, and interacts with almost nothing we know how to detect directly, purely by watching how it bends the light from galaxies behind it. Gravitational lensing didn't just confirm Einstein's theory, it became a telescope for detecting the invisible. One of the clearest demonstrations of this came from a system nicknamed the Bullet Cluster, two enormous galaxy clusters that collided at several million kilometers per hour. When astronomers mapped the visible matter in that collision, the hot gas that glows in X-rays, which makes up most of a galaxy cluster's ordinary matter, it had been slowed down and dragged out by the collision, the way you'd expect two clouds of gas smashing into each other to behave. But when they used gravitational lensing to map where the actual mass was concentrated, the bulk of it had sailed straight through the collision, barely interacting at all, landing well ahead of the visible gas. That's not a subtle result. That's a direct, photographable separation between where the ordinary matter ended up and where most of the gravity actually was. It remains one of the single strongest pieces of evidence that dark matter is a real, physical thing, and not just a mathematical patch invented to make our equations behave. Since then, entire survey missions have been built specifically to do this kind of mapping at scale. Projects like the Dark Energy Survey and more recently the European Space Agency's Euclid telescope spent years photographing millions of distant galaxies for the sole purpose of measuring the tiny statistical distortions gravitational lensing causes in their shapes. No single galaxy's light bends dramatically enough to notice by eye, but when you average the subtle warping across millions of them, a map emerges. A three-dimensional skeleton of where mass, including the invisible kind, is distributed across enormous stretches of the universe. We are, quite literally, building a map of things we cannot see, using nothing but the small print of how starlight arrives bent instead of straight. And it doesn't stop at dark matter. Astronomers now use small, precise versions of this same bending, called microlensing, to hunt for planets orbiting distant stars, planets far too small and dim to ever photograph directly. When a star with an orbiting planet passes in front of a more distant background star, from our point of view here on Earth, the gravity of the foreground star briefly acts like a lens, magnifying the background star's light. If there's a planet orbiting that foreground star, its gravity adds a small, telltale extra blip to that brightening, a tiny second bump in the light curve that reveals a planet we'd otherwise never know existed. Some of the coldest, most distant exoplanets we know about weren't found by seeing them, or even by seeing their star wobble. They were found because their gravity, alongside their star's gravity, bent light passing by on its way to Earth, and left a fingerprint we knew exactly how to read. Let that sink in for a moment. A planet, thousands of light years away, too small and dark to ever appear in a telescope, announced its own existence purely through a flicker in bent starlight. That's not a metaphor, that's the actual method. Bent light is doing detective work that direct observation can't. And there's a strange trade-off built into this method that's worth knowing, because it tells you something honest about the limits of science too. Microlensing events are one-time occurrences. The foreground star and background star drift apart within days or weeks, and that exact alignment will never happen again in any of our lifetimes. So, unlike a planet found by watching a star wobble repeatedly over years, a microlensing planet is usually detected once, confirmed by the shape of that single light curve, and then effectively unreachable for any follow-up observation. Astronomers have to get the measurement right the first time, because there won't be a second chance to double-check it. Some of the loneliest, coldest planets we know of, worlds drifting far from any star's warmth, or orbiting so far out that direct light from their star barely reaches them, were only ever confirmed this way, through a single, unrepeatable flicker in someone else's starlight, bent by gravity into a signal precise enough to read. Now, let's push this to the extreme case, the one that makes gravitational lensing feel almost like science fiction: black holes. Around a black hole, space-time is bent so severely that light doesn't just curve a little, it can curve all the way around the black hole and come back toward you, or get trapped orbiting it in a tight ring called the photon sphere. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, in the galaxy M87, a glowing ring of light surrounding an area of pure darkness. What you were looking at in that famous photograph wasn't just a black hole. You were looking at light from matter swirling around the black hole, bent so extremely by gravity that some of it looped around the back of the black hole and arrived at our telescopes from the far side. We photographed light doing something that, under Newton's old rules, should have been physically meaningless, because light was never supposed to be something gravity could touch at all. That single image took over a decade of preparation and more than 200 scientists working across the planet to produce. The Event Horizon Telescope isn't one telescope at all. It's a network of radio observatories spread from Hawaii to the South Pole to Spain, all pointed at the same target on the same nights, synchronized down to fractions of a second using atomic clocks, effectively turning the entire planet into a single lens roughly the size of Earth itself. The raw data collected during those observation runs added up to more information than could be transmitted over the internet in any reasonable time. The hard drives themselves had to be physically flown to processing centers. And even after all of that, the team spent nearly 2 years independently reconstructing the image using separate analysis methods, refusing to release anything until every group arrived at the same glowing ring from completely different starting assumptions. That level of caution existed for a reason. This was a photograph of a prediction from 1915, finally catching up to a camera, and nobody wanted to publish a mistake with that much writing on it. So where does that leave the paradox we opened with? Light has no mass. That part hasn't changed, and it never will. That's one of the most solidly confirmed facts in physics. What's changed is the question underneath it. The old question was, how does gravity pull on something with no mass? That question assumed gravity was a force reaching out to grab things. The real answer is that gravity was never reaching for the light at all. Gravity reached for space itself and bent it, and light, having no choice but to travel through that space, followed the only straight path left available to it, a path that, to us, looks like a curve. Here's the honest part of this that I want to say plainly, because our channel's whole reason for existing is refusing to leave a mystery hanging without evidence. None of this is speculation, and none of it is a single lucky data point. It's an unbroken chain of confirmation spanning over a century, starting with 2 exhausted Eclipse Expeditions in 1919, running through decades of Einstein Rings caught on camera, through dark matter maps built entirely from distorted starlight, through exoplanets detected by nothing but a flicker in a light curve, all the way to a photograph of a black hole's shadow taken in 2019. Every single one of those pieces of evidence is a different way of asking the same original question, and every single one comes back with the same answer. And notice something about the shape of that evidence, because it's the part that actually makes it convincing, rather than just repeated. These aren't 5 attempts at the same experiment, run by the same team, with the same equipment, checking each other's homework. An Eclipse expedition with glass photographic plates in 1919 has almost nothing in common, technically, with a global network of synchronized radio dishes photographing a black hole a century later. A light curve from a microlensing survey doesn't share instruments, methods, or even the same branch of astronomy with a map of dark matter built from a galaxy collision. Different tools, different decades, different teams who in some cases never spoke to each other, all independently colliding with the same conclusion. Mass bends space, and light has no choice but to follow the bend. That's what makes this something closer to a verdict than a guess. If this is the kind of investigation you actually want more of, us tracking down the eclipse records, cross-checking the exoplanet detection papers, verifying the black hole imaging data instead of just repeating a cool-sounding headline, that takes real research hours behind the scenes that don't show up on screen. If you want to help keep that kind of digging sustainable, a super thanks on this video goes directly toward the research time these case files take, and it genuinely matters more than the algorithm numbers do. No pressure either way, but I wanted to be upfront about it because you deserve to know where the effort in this channel actually goes. Before you go, I want to leave you with the actual next question this one opens up, because it's the one that even physicists argue about at conferences. We've now shown you with real photographic evidence that mass bends space and light follows that bent space. But we still haven't answered the far stranger question sitting underneath all of it. What is space, physically, that it can be bent at all? Not metaphorically bent, the model we use tonight, the paper and the bowling ball, but actually physically warped, the way Einstein's equations describe. Is space a real substance with properties we can eventually measure directly, or is curved space just the best mathematical language we happen to have for something we don't yet have a physical picture of at all? That's the next file. And the honest answer is, right now, nobody fully agrees. So here's what I want you to do before the next one drops. Think about how you'd even test that question. If space itself can bend, could it also ripple, vibrate, or wave, the way water does when something disturbs its surface? Comment your best guess below. No wrong answers here, because this is one of the genuine edges of what we currently know, and I'd rather hear what you think before I tell you what the evidence actually says.